So what I can do is maybe put my laptop here, and the Zoom will get the.
Okay, you try that?
Yeah, but I just don't know how to. I won't be able to monitor anything.
Okay, that's fine. I think. Okay, can everybody hear us online?
Yes, we can hear you.
We'll sort it out, don't worry.
Yes, you're now audible.
You're now audible.
Okay, great. Let's get to it.
At least now we know. Thank you. And I'll pass this feedback back to the audio people.
So the audio is going through the laptop.
So I need to sign with the laptop.
Well, I think as long as you're here, the audio should be fine.
Yeah, Mac is usually quite forgiving, so I'll just sit in the corner.
Is that fine like that?
Perfect.
Okay, there you go. Okay, so let's try that again. It's part two of the Oxford. Oh, wow.
We're not quite there, guys.
We're gonna have a third go. A new sill is coming in.
Okay, how is it now?
Okay, I think we're in business.
Are we still audible there online?
Yeah.
Okay.
Okay, great. Okay, let's get going. So I'm pleased to introduce Rhiannon Ackland. Rhiannon is John Blundy and Elena Melikova's PhD student. She has an undergrad degree from Cambridge and is now based at Oxford, completing her PhD. So which boat team do you support?
I do support Cambridge still.
Supports
So,
Cambridge, okay.
I'll get that one quiet.
And Rhiannon is going to be exploring during her PhD possible processes that led to the formation of the magnetitite layers in the Bushveld. So for the last week or so, we've been going around to different sites, sampling upper zone material for her project. So the floor is yours. Enjoy.
Thank you. So thank you very much for having me. Yeah, I'm going to discuss some post-magmatic processes in the Bushveld and some experiments I've done on sort of a simplified chemical system to explore the textures of replacement features. I'm at the university where the Bushveld needs no introduction, but for completeness, just in case, I figured I should give a little bit. So the world's largest layered intrusion. I'm focused on the upper zone, which is this purple unit here, which contains layers of near monomineralic magnetite, magnetitite. And the importance for studying this, as again, I'm sure that you're all aware, is that the Bushveld is incredibly enriched in many critical metals, including the vanadium of the upper zone, which is among the 18 metals designated most critical by the UK government. But more fundamentally, the Bushveld is a great laboratory for exploring some fundamental igneous petrology questions. To what extent do the igneous products that are preserved today reflect primary magmatic features? Or in a mushy zone, sort of the other side of the coin, what's the extent of subsolidus element redistribution? So many people maintain that the Bushveld intruded as a large liquid-dominated magma tank. And even if that were true, I think it's important to question whether the Bushveld had a mushy period of its life anyway. So the Bushveld is a huge intrusion. It's got a large amount of heat, sensible heat, latent heat. And so it's going to have a protracted cooling history. And studies of paleomagnetic reversals show that it took 500,000 years for the upper zone to cool from its liquidus to 580 degrees, the Curie temperature of magnetite, with 300,000 of these years occurring subsolidus. And it obviously has an even more protracted cooling history if we consider cooling below 580 degrees. So there's a long period of time over which the upper zone was below its solidus, therefore a solid dominated mushy system, and reactive flow processes could be significant. So when we are considering this, rather than orthomagmatic processes in a liquid-dominated system where crystals move relative to the melt, settling out of dense crystals, flotation of potentially buoyant crystals, I'm interested in paramagmatic processes where fluids move relative to crystals. And these fluids, which we've been shown agents of mass transfer, can include late stage near solidus melts, subsolidus brines and fluids, and also I'm interested in the separation of immiscible liquids. So in the upper zone, potential separation of a silicate rich and an iron rich portion of the melt. So the sort of key questions that in my PhD I'm interested in addressing are what were the agents of mass transfer in the upper zone? What was the direction of this mass transfer? Are we considering buoyant fluids rising? Are we considering a dense iron-rich melt that's sinking? Is there any lateral spread of melts and brines, maybe along impermeable horizons? And these processes, to what extent do they cause redistribution of elements? And of particular importance, to what extent do they redistribute critical metals? So there is several lines of evidence that there were briny fluids present in the Bushveld. So in the quartz of the Morensky Reef, Zatova's paper highlights the presence of multiple fluid stages, including a subsolidus hypersaline brine, which was metal bearing, so has the potential to cause significant redistribution of metals in the critical zone. And similarly, a currently unpublished study by Katie McFall that's been presented at conferences reveals that the northern limb of the Bushveld is full of fluid inclusions that show high carbonate contents, and that these are all metalliferous as well and could cause redistribution. Okay, so I apologize, there seems to be some slight formatting problems. But yeah, so the place to start, if we want to understand the metasomatic processes of reactive flow, we've gone back to the classic theory of metasomatic zoning from Krzyzewski, publishing in Russia in sort of the 1950s to the 1970s. And there are two sort of main step forwards that he contributed. The first is that normally Gibbs phase rule is applied only to closed systems, whereas Korzynski wanted to apply this to metasomatic systems where your fluid is entering and exiting the system. So you have a fundamentally open system, and so closed system thermodynamics can't be applied. So he suggested the theory of local equilibrium, or the assumption of local equilibrium, I should say, which is where you consider a small enough volume that on this small volume, all your components are in equilibrium. So in a metasomatic system, this generally means that you consider that your fluid is in equilibrium with the solid material that it's in contact with. And then his second sort of great contribution was adaptation of the Gibbs phase rule, which normally relates degrees of freedom to components and phases. So Korzynski suggested that there are two types of component in a metasomatic system. You have what he termed perfectly mobile elements. These are sometimes referred to as externally buffered components, components whose chemistry is controlled by the infiltrating fluid. And then you have perfectly inert components. These are generally fluid immobile, internally buffered components whose abundance is not affected by the infiltrating fluid. And therefore, if you consider that the perfectly mobile components you have to constrain these by your fluid composition, this increases your degrees of freedom, and this results in the fact that your phase assemblage has to decrease in number of phases. And therefore, that in metasomatic rocks, you tend towards rocks with very low number of phases, with monomineralic and bimineralic rocks being common. And another implication of this is that the interfaces between these metasomatic zones have to be very sharp. And this is seen commonly in metasomatic skarn deposits. I should mention he also predicted scales of up to 10 meters thick, which again is consistent with what we see in skarns. So skarns form where fluids from intruding plutons infiltrate through and react with carbonate country rocks. And this results in monomineralic zones of wollastonite, garnet, and pyroxene. And here is from John's favorite location, the Adamello, an example of one of these veins. So we have the tonalitic intruding rock and the marble original carbonate rock. And you see these diopside and garnet monomineralic zones with sharp interfaces between them. And you can also have similar serpentine magnetite systems as seen in Iran. Yeah, so we saw rocks that looked very similar to this in the marginal zone of the Bushveld on our field trip, where marginal mafic rocks contained large xenoliths of calc silicate country rocks. And you can see that along some of these margins, we saw diopside and garnet. Here they were bimineralic zones with very sharp interfaces. A reactive flow has been proposed elsewhere in the Bushveld. So Wolfmeyer has proposed that the mottled anorthosite in the critical zone, that this represents sort of a proto-norite that's been infiltrated with silica undersaturated fluids, which have leached silica from the mafic components, leaving the plagioclase intact, resulting in these leftover mottles. And some of the evidence comes from this is the albitic zoning in the plagioclase adjacent to the mottles and the olivine-rich cores. And similarly, where there's olivine spinel symplectites, these have been suggested that you had infiltration of a fluid that was undersaturated in the components of chrome spinel, causing resorption of that chrome spinel and these symplectite textures, whilst also being silica rich, causing the peritectic reaction of olivine to form OPX. And we saw several examples from our field studies and also mineral studies that show that there were late-stage fluids present in the Bushveld. So here I have, Billy's pointer working. So I have sample from the upper zone where it's common to see biotite and chlorite, so hydrous minerals present between magnetite and plagioclase regions, and also chromite often contains fluid inclusions that show hydrous minerals, hornblende and phlogopite. And also in field outcrop, we saw numerous pegmatites. So these are just some examples of pegmatite we saw in the critical zone at Glas River, and also pegmatites as part of the IRUP pipes, the iron-rich ultramafic pegmatites of the Bushveld. These intrude through the critical zone and the upper zone. And also, I didn't have a chance to put these in, but we've had some great sampling days at Roven Mine in the Western Limb, looking at the upper zone, and pegmatites, late-stage pegmatites were really abundant in these regions too. Yeah, and so the presence of these biomonomineralic layers, like the magnetite layers and the chromatite layers, fit well with Krajinski's theory that we have a metasomatic system that is meaning that you have to specify more degrees of freedom, and so you have a lower phase assemblage. We also saw evidence for felsic segregations in the critical zone. So this picks out a region of felsic melt within a norite, and rather than being intrusive, it has these sort of blobby, rounded textures that suggest that it's a separation rather than an intrusion. And we also saw evidence for downwards infiltrating iron-rich melt. So here the mottled anorthosite in the critical zone sometimes showed these dendritic oikocrysts of pyroxene. Yeah, we think looks very much like a downwards infiltrating melt. So what I've done so far in my PhD is explore a very simplified reaction, the reaction of quartz, which is silica oversaturated, with olivine, which is silica undersaturated, to form rims of orthopyroxene. And this is a very well-known reaction that's driven by a change in chemical potential. So if you have chemical potential of MgO against chemical potential of SiO2, you can see that end statistic orthopyroxene falls between quartz and forsterite. So the chemical potential gradient here is what's driving this reaction. But what we were interested in is the sort of how this process is taking place on a fine-grained scale, what the textures of a replacive reaction like this look like. So I've performed some experiments in a piston cylinder. So this works by applying a pressure to a sample, and you can heat it to up to 1,600 degrees and pressures of 3 to 30 kilobars. So the conditions I ran at were both 800 and 1,000 degrees and at 1.5 gigapascals. And we had interlayered olivine and quartz powders, which in a gold capsule, so use a gold capsule so that the system is closed, particularly water can't get in and out of the capsule. I did these experiments for a range of length scales and a range of water contents, both nominally dry and with 1 weight % water. So a caveat here is that nominally dry does not mean a completely dry system. So doing experiments in the UK, it's extremely humid. It's always raining. You can't get a completely dry, system. So because these were crushed powders, I get water absorbing from the atmosphere into the powder. So there is still a small amount of water present. And at 1,000 degrees, all of my experiments showed growth of orthopyroxene rims between olivine and quartz. And these showed a range of textures. So always the olivine OPX interface shows these sharp, quite planar interfaces, whereas the OPX quartz interface is much more variable. It could be also sharp and planar, like the olivine interface, or it can be jagged with the development of subhedral orthopyroxene crystals. And experiments that I ran for a long period of time, 5 weeks, or in a water present system, I saw void space opening up at the quartz interface. The void space is opening up due to the negative volume change of the reaction. And into this void space, we see large euhedral crystals of orthopyroxene growing. Another interesting feature of the experimental results is the distribution of iron within the orthopyroxene rims. You might expect that because olivine obviously has much more iron than quartz, that the orthopyroxene would show a diffusion profile with high iron adjacent to olivine and low iron adjacent to quartz. However, this is exactly the opposite. Also notice this sort of patchy texture to the ion zoning, which, with comparison from EBSD studies of similar systems, we think this reflects the grain size of the orthopyroxene. So there's iron-rich rims, magnesium-rich cores, to a polycrystalline orthopyroxene rim. So this tells us one of the first sort of key findings about these replacive textures is that there's a complete overprinting of the primary textures. So if you have this sort of original interface image with olivine and quartz adjacent, and the orthopyroxene is completely overprinting this, it's not inheriting the original crystal structure. We have sub to euhedral OPX crystals developing. We also have a change in grain size. The powders were sieved to be between 50 and 100 microns, but the grain size in the orthopyroxene is far smaller than this. You can also see that the quartz is recrystallized to be in textural equilibrium. Many examples of sort of 120-degree boundaries of quartz grains. Obviously, they're opening up a void space, as I mentioned. And very interestingly, the OPX is not limited to the initial interface between the quartz and the olivine. In some places, we saw it migrating along the quartz grain boundaries, and even in some places developing sort of subhedral OPX crystals in these places. So there's a complete overprinting of any primary magmatic textures we might see with secondary replacive textures.
Sorry, Rhiannon, is the right-hand one water-based?
No, this is a normally dry. Another interesting feature, all the images I've shown you so far are from my experiments at 1,000 degrees, but actually at 800 degrees, no OPX rims were observed. And my experimental capsule, there's quite a large thermal gradient inside it. So my capsules were about 1 centimeter long, which probably sounds quite small to most people, but to an experimental petrologist, these are outrageously large capsules. So I have a huge thermal gradient of up to 100 degrees within the space of my capsule. So whilst the region with the thermocouple is at 1,000 degrees, my experimental rooms were generally higher temperatures, around 1060, and so in the vicinity of the wet melting point of quartz. And so the fact that at 800 degrees, where we're far away from the wet melting point of quartz, we see no reaction, this suggests that a small degree of melting is required for these reactions to take place, whether that be melting of the quartz completely, or what I think is more likely is a small amount of pre-melting behavior, where you only get thin melt films forming along crystal boundaries. So a little bit about the mechanism that we think these rims are grown by. So rather than a simple diffusive system where cations are diffusing from the olivine through the OPX to the quartz interface to cause crystallization of orthopyroxene, we actually consider that an interface coupled dissolution reprecipitation mechanism is occurring. So this is where, if you have the classic example of this is you have a parent phase, BX, which is in contact with a fluid rich in a different cation, A, and these react to form the product phase, AX. And rather than a diffusive exchange of A and B between the fluid and the parent, they suppose that the outermost layer of the parent phase dissolves in the fluid, and this causes saturation of the parent phase and precipitation of that parent phase. And the rates of this dissolution and precipitation are coupled. This reactive interface then moves throughout the crystal, slowly converting it to the product phase. And the features characteristic of this mechanism are very sharp interfaces between the parent phase and the product phase. The generation of porosity is required in the product phase so that a fluid pathway is maintained between the bulk fluid and the fluid that reaches the reaction front that causes the dissolution of the parent. No worries at all. You see a lack of diffusion profile in the parent mineral phase, so you'd see no diffusion profile in the cation B in this parent. And the product phase can be either polymineralic or epitaxial, depending on if you have a high degree of similarity between the crystal structures of the parent and the product, you'd see epitaxial growth and perfect inheriting of the parent's crystal structure. But if there's a large degree of mismatch, then you get polymineralic rims instead. And the way that they have sort of shown this to be the case in the form of porphyroblasts in metamorphic rocks is that they've done doped experiments with isotopes where they showed that as well as exchange of the A and B cations, there's also an exchange of the X here, the anion, and you're getting incorporation of the fluids isotopes within the product phase. So many of the features of the ICDR mechanism we see in my experiments. As I mentioned, the olivine OPX interfaces are always sharp and often sharp at the quartz interface. I do see the porosity generation within my rims. You can see here some examples of this. There's a lack of diffusion profile in the olivine. There's no diffusion profile in magnesium and iron towards the OPX interface. And we don't really expect any diffusion profiles in the quartz. And due to the high degree of mismatch between the OPX crystal structure and olivine and quartz, I see this fine-grained polymineralic growth of orthopyroxene, as is picked out by the ion zoning. So an interesting feature of some ICDR mechanism experiments is the formation of zoning within the product phase rim. So in these experiments, Borg et al. Have put crystals of calcite within a fluid that contains both phosphate and arsenic. And so as the reaction proceeds, the calcite develops a rim of apatite. And initially, this apatite is phosphate rich and it contains low proportions of arsenic. But as the reaction rim moves into the calcite, the proportion of arsenic in the apatite increases. And this is thought to be because the porosity that's generated within the rim is only microporosity. Sorry. Oh, gosh, I hope the talk's not that boring. Okay, so sorry. So the rims become more arsenic as they move into the calcite. And we can think of this a little bit like fractionation. The arsenic is less compatible in the apatite rim than the phosphorus. And so as you move into the the reaction front moves further into the calcite, the arsenic is built up in the fluid, causing the precipitation of more arsenic-rich material, with exchange with the bulk fluid restricted due to the nanoporosity of the rims. And as these experiments ran to completion, they did eventually equilibrate and become homogeneous apatite in equilibrium with the fluid. But this trend is very similar to that which I see in my rims with the distribution of iron. And actually, I've done just a little bit of a back of the envelope model of this. And if you suppose that the olivine and the orthopyroxene that forms at the olivine interface is in chemical equilibrium in terms of the iron number. As I mentioned, this means that the orthopyroxene has a lower iron number than the olivine. This then releases excess iron into the fluid, which due to the formation of void space gets sucked into the quartz interface. If there's not a one-to-one partitioning of iron between the fluid and the orthopyroxene that crystallizes at the quartz interface, this means that the fluid at the quartz interface becomes increasingly iron-rich as the reaction proceeds. And you can build up increasingly iron-rich orthopyroxene at the quartz interface, as is seen in the sort of arsenic phosphate experiments done by Borg et al. And so here I've just done a couple of simple simulations with different partitioning of iron between the OPX and the fluid, which you can compare to sort of a classic profile across my orthopyroxene. And some of my rims show maybe a clearer signature of flattening out towards the olivine interface. And obviously with the probe, the excitation volume means that these profiles are slightly smeared. And so one of my next steps is to consider sort of a more quantitative, detailed model of this reaction, where at each interface, the OPX interface is allowed to move at a different rate to the quartz or olivine interface. And this allows for us to express the volume change of the reaction and express the creation of void space, with the orthopyroxene allowed to add vector within this void space to control where it's opening up. And due to the inclusion of void space, you can express the fluid volume flux within the sort of OPX region and also from the quartz and olivine into the void space. And so I'm hoping to use these models to firstly compare the rates of orthopyroxene rim growth to see if I can recreate that trend and see if this ICDR model is viable. And then add iron as an extra component to see if it can explain the iron zoning. But unfortunately, I don't have those results yet, but that's sort of one of the next things I'm going to be working on. Yeah, and then so I just wanted to finish on sort of raising some points of similarity between the experiments that I've done and some of the textures that we've seen during our Bushveld fieldwork over the last 2 weeks. Firstly, as I mentioned, you get complete overprinting of the primary textures in my experiments with these very polycrystalline orthopyroxene rims. And one of the outcrops we saw of the marginal zone had what looked like beautiful large plagioclase oikocrysts, but actually they're very finely polycrystalline, much in the same way, so potentially completely recrystallized, and you've lost that primary magmatic texture. And secondly, I see that it's possible to get migration along grain boundaries, even away from the original interface. And so thinking about the movement of fluid, we see similar things where you have, as I mentioned, this what looks like downwards infiltration of a dense fluid and sort of oikocrystic pyroxene dendritic growths this way. And I'm hoping to link these sort of oikocrystic mottles to this sort of process of growing along grain boundaries. So yeah, so just to sort of sum up what my preliminary experiments have found is that primary magmatic textures can be completely overprinted by the replacive features. These are very rapid processes at near solidus conditions. In 2 weeks, I'm getting orthopyroxene rims that are already 40 micrometers thick. And so over the protracted cooling history of the Bushveld, this suggests that there's possibility for significant replacive textures of a large scale. And one of the key observations from my experiment that can be that I'm hoping to compare to things that we see in the Bushveld is the development of this distinctive zoning of the sort of major and minor cations, to sort of use this as a test for the presence of these metasomatic processes. So yeah, so thank you all for listening, and I want to say a big thank you to Antoine and Phoebe for some great discussions in the field, but most of all, a huge thank you to Ben for playing such a big role in organising the field work and for sharing some great ideas. Thank you.
Thank you very much. Questions?
I'm interested in the MGF zoning found in the OPX. My silly intuition thought it would be the other way around. But what I'm thinking is you must have started with some kind of an intermediate olivine composition. You didn't specify what that was.
I apologize. Yeah.
So what was it, about 50-50 or?
No, so I used natural olivine samples. I use San Carlos olivine.
But
So
what was the composition of this olivine?
I think it's around phosphorite 90.
Phosphorite 90. Okay, so what I'm thinking is that olivine is much happier when it's iron rich and in the presence of quartz. So in fact, pure phyolite is completely stable with quartz, and that's why I would have figured that your olivine would have been happier with an iron rich neighbor, not the other way around. So I'm puzzled by that, and I guess you are too.
Yeah, this is something. So initially, I was thinking of this as a diffusive reaction. You have the overproduction rings growing, and you have diffusion of cations from olivine towards quartz, diffusion of silver.
Maybe you could try doing experiments at different olivine compositions, getting more iron rich, and see what the hell happens.
Yeah, I think that would be potentially interesting. I presume we would see a sort of a similar trend until you reach the point where the olivine was so phyolitic that it became stable with quartz. But yeah, it certainly is. So we chose the San Carlos olivine to be as phosphorytic as sort of as reasonably possible for a natural sample.
You wouldn't see anything if it was pure forsterite.
So we wanted to start out with a system where the chemistry is extremely simple, so we could look just at the textures. So actually, the ion zone we saw was a bit of a surprise. It was not a result we were initially expecting.
Cool.
Questions?
Sorry, I wanted to ask about the volume reduction. How big is that?
It's a 6% volume reduction.
And with that, I mean, this is a capsule.
Yes.
And we're talking, I mean, over the size of the Bushveld, that must have a dramatic effect on the volume of, I mean, these are huge volumes.
Yeah, so this is something I was thinking about in the capsule. Obviously, the void space stays as probably fluid for void space.
So the capsule doesn't contract.
No, no. So I suppose what we think is happening is that the fluid is filling those void spaces. But in a natural system, you'd expect that fluid to escape. So that's the purpose of the gold capsule, is to keep the fluid inside. But you'd expect those fluids to escape, and yeah, in the case of such a large volume reduction, potential then something can collapse if the overlying rocks. But then obviously it would depend on what your reaction was, whether
there are other reactions that have similar. I mean, 6% a lot.
Yeah, so this is the sort of the one I've looked at. The ICDR works in cases where you have a volume reduction, but even when you have a volume increase of reaction, these reactions can still take place via ICDR, and obviously the question over porosity generation in the rim that's required for the reaction to keep going, they call upon sort of that you can, based on solubility, you can never precipitate quite as much of the product phase as the parent phase was solved.
Interesting, thanks.
I have a different kind of question. In the uppermost part of the Bushveld, so the upper zone, you do get phyolite with quartz, and it's magmatic, clearly magmatic quartz from the textures. And in there are beautiful fluid inclusions, and are magmatic fluids in the quartz. And in there, you find a lot of methane. What the hell that's doing in there, I'm not sure. I had a student doing a master's on this. I'm not sure he answered either, but that might be relevant because you mentioned fluid inclusions in your beginning, and it was all CO2 and H2O, I guess.
Yeah.
But methane is important.
Okay, yeah, I'm not aware of the fluid inclusions in those quartz grains, but I wanted to make the point that the Bushveld was cooled over a long time. There are the presence of these briny fluids. So, the potential, but basically I expect that these post-magmatic processes are happening. It's just to what extent they're happening, to what extent are they overprinting the primary features.
Questions?
We have one from Grant online. Okay, so you can unmute and speak, Grant.
This is one.
Hi, everyone. Rhiannon, I'm a bit confused because I thought you were going to be talking about magnetitite layers.
Grant, are you still there? Do you want to ask a
Yes,
question?
I am, yes.
I'm not hearing you on the speaker, so you might have to write it out.
Okay, can you hear me? Can anyone hear me? I've got my audio on. Oh.
In the meantime, I can ask a question. Richard, so I was just wondering, I was struggling to follow, but at the end there, were you saying maybe that you showed some examples from the Bushveld, like the very coarse grained, is it poikilotic or yeah, like on the bottom right there, oikocrysts, like are you thinking that it's these reactions are pseudomorphing things that are already there, or is that whole texture, do you think, the product of this of the process?
That's a good question. This was more to highlight sort of the direction I want to go next. Okay. So it's not something I've thought about completely. I'm expecting this sort of texture to me doesn't look pseudomorphic because this is not the primary texture that I'd be expecting. And I think potentially the point I was trying to make is that in my orthopyroxene limbs, I'm not limited to the initial interface. So things can migrate away from that. So you're not necessarily limited to pseudomorphing for these replacive features. They can migrate away from those original positions. Has Grant got?
Hawthorne, try again. According to my computer, I'm not muted. Can you hear me?
I don't think our speakers are working, Grant. You might have to write it out.
It's too long and complicated. Don't worry. My speakers.
Here we go. Okay, just repeat it. I'm just trying to put it through the laptop speakers. Any more questions?
You have a picture of CPX and OPX.
No, OPX and all. Oh, she had, okay.
But an actual, so we were looking at a place where there were like these little florets.
Oh,
Yeah.
Yeah.
I've got a neutron tomography of some core that shows that in 3D. It's really interesting.
That's not going to let me skip back.
Yeah,
again,
no, it's no problem.
So sorry, you said you have a neutron.
Neutron tomography data on some cores that go through some of these florets, for lack of a better term, in 3D.
Oh wow.
Yeah, so it's really interesting to see. Yeah.
And what sort of shape are they in?
They're little trumpets.
Oh, okay.
Yeah.
Interesting.
Very
So
interesting.
sort of maybe like a smaller scale inverse shape of these downwards.
No, those dendrites. So this is I'll find a picture.
Okay,
of it. Yeah. Did the question come through?
No.
Yes.
I did.
Ask a question. My own student. Rhiannon, right at the beginning, you showed some data on the fluid inclusions that have been found by GEOTALK. You showed something that I hadn't previously realised. I don't know. Are we allowed to go back to slide? I don't know where it was.
It's struggling to open.
Maybe if you quit, and then we're getting there.
That's always bad.
There, that's the one.
All right. That's
It's not letting me.
Can't
it
even
is
quit.
already, yeah.
Wow.
But anyway, yeah.
Oh, are we getting closer? Yes.
Maybe
That, stop. That fluid has 18% iron.
Yeah, they're extremely rich in metals.
Isn't that incredible? So if you want to move iron around, that thing is going to be a great iron mover.
Yeah, so this is, so interestingly, so this is in the critical zone.
Oh, I can
So
see. Yes.
the question of whether you could make an iron-rich fluid or an iron-rich melt buoyant enough to reach the upper zone to interact with the magnetite layers is an interesting question, but whether you could have one that's rich in volatiles or yeah, I think that's the point of they make in the paper is that these brines are extremely metal rich.
Yeah.
I'm just curious because you show the IRAP, so the contact, the sharp contact between the peroxenite and anorthosite, and then you also have the magnetite alternated with the anorthosite, and then you have chromite alternated with anorthosite. So it looks like this anorthosite is playing a role in all of this.
Yeah.
And we don't have this example of the pyroxene and olivine because here the mineralogy is a little bit different.
Yeah.
But do you think it's the same kind of process that is forming there?
Well, I think an interesting question in the anorthosite is sort of you're missing a lot of iron in that in an anorthositic rock, and where could it have gone? And that's why the upper zone where you have these interlayered anorthosites and iron-rich magnetite layers, I think is very interesting. How do you remobilize the iron in this system? And you mentioned the IRUPs, so we were quite fascinated with the IRUPs when we were in the field, particularly the interaction between the IRUPs and the mottling in the anorthosite, whether these are in some way related, and whether the IRUP is actually acting as a source of fluid that could then be infiltrating through permeable boundaries in the anorthosite. This is something I'm quite keen to explore. We've taken a huge number of samples of these materials that I'm going to go and study now that once we're back in Oxford. But that's a sort of one of the key questions I want.
Time for one final question? No? Okay, great talk, Rhiannon. Thank you very much.
Yes, sure.